Okay, all right. Shall we get started? Everything else going okay? All right, week 4. How about we talk about GPUs? We're going to talk about some GPUs today. All right, so here's what I thought I'd do today. I wanted to start with just a little bit of history on how we got here with modern GPU computing, which basically is like, how did these chips that folks like NVIDIA and AMD were producing largely to play Quake, how did they get us to a point where NVIDIA is a $1 trillion company that's much, much bigger than Intel and everybody's fighting over how to buy these things? Okay? So I'm going to give some history, and then we're going to do a conversation about how to program these GPUs using a language that's provided by NVIDIA. I mean, most people write GPU code in CUDA these days. CUDA, you're going to find very similar to ISPC. In fact, ISPC, if you read that blog post about the history of ISPC, actually is a reaction to CUDA. They were like, oh, people are programming GPUs with CUDA. Why can't we program the same way on CPUs? And so they hacked up ISPC in response. So the programming model should be pretty familiar. And then we're going to talk a little bit about how modern GPU architectures work and how they run that CUDA code. So I want you to think back to basically the first week of class, so the second week of class. And we talked about, and you've done a written assignment now, really working through the details of ideas like multi-threading and SIMD and multi-core execution. And you've had some experience running that code on CPUs. So the first thing I want to tell you is that there's not going to be anything new today. It's the same ideas, multi-core, SIMD, multi-threading, and stuff like that. They're just going to be deployed at a little bit bigger scale for a modern GPU. So in some sense, no new concepts today, just another instantiation of those ideas. All right, so how many of you have taken, looking for familiar faces, have taken 148 or sit around for 148 after this, or 248 with me or something like that? Okay. So you know, some of you know a little bit about graphics. You know a little bit about how pictures are rendered. For the rest of you, here is CS248 in like 5 slides. So the goal of an original GPU design was to solve one specific problem. And that one specific problem was, given some mathematical description of a scene, and that mathematical description was kind of the geometry of surfaces, the location of lights, the position of some fake virtual camera. Perform a simulation, simulate the bouncing of light in the scene, simulate all these materials, and give me a picture of what I would have seen if that was a real camera at that location. That was the goal of a graphics chip. Okay? And graphics chips do that quite well. You know, here's an image. This is actually a pretty old image now. It's 2015. This image, 60 frames per second easily on a high-end GPU in 2015. If we step forward to a little bit more modern graphics, this is something that we can render in real time on unreasonable high-end GPUs. So this is from the Nanite demo from Epic. And the workload, like the actual computation, if I asked you to write some software that ran, that computed this stuff, is pretty simple. And so here's CS248 in maybe 45 seconds. So the name of the game is to render a surface like this. And so the way you work with a GPU in the old days, or at least if you're doing graphics, is you provide it some notion of what your surface is. And the surface that the representation that we typically use in computer graphics are triangle meshes. So you give the pipeline, you give the GPU a list of points in 3D space where all your triangle vertices are. And you basically ask the GPU, given these points in 3D space and given like a camera position or orientation, hey, GPU, you go do a little bit of math that we teach you in 248 to figure out where on screen all of these little vertices project onto. So it's like if I held up a camera right here, where is every vertex going to be on screen? And for every pixel in the image that's covered by these triangles, once I know where they're on screen, I need to compute the color of that triangle. And if I want to compute the color of the triangle, if you look around this room, the color of all the various surfaces in the room, it comes from what material they're made out of. And if you think about, like, if we have to simulate how light is bouncing off these chairs or off this bamboo texture or off like the shiny metal of the door handles, you quickly go, wow, there's a lot of different materials in the world, right? And early graphics said, oh, and like, here's an example of a bunch of materials. These all kind of look alike, but, if we can get pretty sophisticated with our materials, like if we look at the glints in these shoes, if we look at the fact that human skin, light enters the skin, bounces around a lot, and comes out somewhere else, simulating how light bounces off these materials to just compute the color of these triangles, people were like, the materials of the world are so different, we just want to write a program that does this. It's not like we're going to say the color is red or the color is blue. We're just going to write a program. And so in the early 2000s was the time when people started developing these little programming languages that will run for every pixel on screen, which, given some information about the current material and the orientation of the surface. So the code doesn't, the details of the code doesn't really matter, but it's like there's like a coordinate, a 2D coordinate of where I am on the surface. There's the normal of the surface, which is like the vector pointing away from the surface. And there's details of like texture maps, which if we just do a little bit of work, we have algorithms for computing given the orientation of the surface, given that I want like this image to be wrapped over the chair surface. If I run this code for every single pixel on screen, I compute a color. If you look at the output, return vector is a color. This is like KD is a vec3 RGB, and that last component there is alpha. Running this function for every element or every pixel gives me an image that looks like this. So there's just basic data parallel computation like we've talked about. For every pixel, compute some inputs, and then run this completely independent function on every pixel to compute some colors. That's kind of CS149 in a nutshell. And so the reason why GPUs started adding multi-core and adding SIMD is because they were like, I got to process a 4K image, millions of pixels, and I need to do it 60 times a second or more. I've got to get through hundreds of millions of pixels to billions of pixels per second. So they just started like adding more and more GPUs to compute color of more of these. They added more and more cores and more ALUs in order to compute the color much more fast, much more quickly. Okay? And so if you go back about almost exactly 20 years now, and we go back to lecture 1, remember we said that like there were more and more transistors. The green line was the number of transistors per chip, but all these ways to turn these transistors into faster single-threaded processors were kind of not working anymore, right? We couldn't ramp clock speed because like power was going through the roof with 4 gigahertz processors. We couldn't do superscalar anymore because like there was no ILP to find in threads. But these GPUs were adding more, had already gone to parallelism. They were just going to add more and more cores as the green line went up. And so some folks around the country, some folks here at Stanford, some folks at the University of North Carolina, and a few other places said, well, Intel's processors are not getting any faster. But these GPUs are adding more cores every single time the transistor doubles, and they can run code. They run these little programs that compute the color of things. So some folks just started to hack. And they started to hack by doing the following. Let's say you were rendering an image to a screen that was 512 by 512. They said, here's what we're going to do. We're going to render 2 triangles so that the entire screen is covered by those triangles. And then we're going to, instead of running a program that computes the color of something, we're just going to have that program do something interesting, like time step a particle in a physics simulation, or do some protein folding or something like that. So there was this big hack where you actually drew 2 triangles on the screen, basically to create 512 squared function calls. And then inside this thing that was supposed to compute the color of a surface, you just said, do something that I want it to do. And so there are these hacks. Like if you look at the dates on these, about 20 years ago, people said, oh, I can like treat that RGB output as like XYZ position of a fluid simulation or something like that. So people started hacking, and they're like, these GPUs are really, really fast. We can actually run a lot faster than what we would do if we ran threaded code in C++ or something like that. Now, there was a research project at Stanford in 2004, which kind of said, wait a minute, like, this is a hack. This is pretty stupid, right? Like, if we're going to use these things as parallel processors, and we all know about data parallelism and all this other stuff, could we just have a proper programming system to just treat them as such, right? And so there was this project where folks used the data parallel programming model, where you just which we'll talk about in more detail on Thursday, but the main idea is there's some function here, like in this case scale, which takes as input an A and a B and just scales A by amount. But scale is evaluated not on scalar values, but on collections. So I'm making up some syntax here. Think about this as like a vector of 1,000 numbers, and you're applying scale to every element of that collection. So this was called like the stream programming model or data parallel programming model. And this code, which was actually valid code in this language called Brook, actually got compiled source to source to this graphics program that drew two triangles and then used the GPU. Again, like less of a hack for the users, but a total hack from the implementation standpoint. Okay. So around this time, NVIDIA was making faster and faster processors. They were starting to think about, well, maybe these things can do more than just graphics because they run code. And so inspired by projects like this and others, NVIDIA says, you know what, we should actually just do it ourselves to allow people to write general purpose code for these things, because the chip could already do that. So if we remember a little bit about how CPUs work, imagine you had a multi-core CPU here that has 2 cores, 2 total execution contexts. How do you run some code on this processor? Or in other words, what does the operating system do? Like, actually think through it. Imagine you were taking, let's hypothesize. Many of you probably have not. But imagine you're taking an operating systems class. And as an operating system, you're supposed to, let's say we want to run 2 different programs on this 2-core machine. How do you get that program started?
So if you have 2 different programs, you ideally have like 2 stream instructions.
Yeah, so I have 2 programs. I compile my program. And then as the operating system, if I want that program to run, what happens? What do I do?
Kind of parse each stream and assign it to each of the cores.
Yeah, so the operating system is going to say, here's instruction stream 1. Hey, core, let me initialize the value of your registers. I'm going to set the next instruction to execute to the top of that program. You just tell it go. So it runs a thread here. And if you want to run another thread, the operating system might say, I've got this other thread from this other program. I'm going to run it here on core 0. So you kind of say, here's your program binary. Initialize the state of the thread and go. And you do this 1 thread at a time. Okay? And that's exactly what an operating system does if you took an operating systems course. Okay? That's how we run code on CPUs. But how we ran code on GPUs before NVIDIA said, hey, we need to give you access, was there was no run a thread. It was literally the command you sent the GPU was draw these triangles and use this program to compute the color of the pixels after you've figured out what pixels need to be colored in. And so that interface to the GPU was this thing we call the graphics pipeline that has all the algorithms of CS149 in it. But the interface to software is literally, software gives the GPU a list of triangles and a program to compute the color of the surface and a location of the camera, and then the pipeline just runs. And it runs that program whenever it needs to compute the color of a pixel. Very, very different way of thinking about how to kick off computation. So in 2007, NVIDIA said we need something kind of in between those two. It seems stupid to draw triangles to use our processor to do things that have nothing to do with graphics. And at the same time, we don't really want users to create all these different threads, because all these different threads aren't going to run very well on my GPU that has 32 wide SIMD and has terrible single-threaded performance and stuff like that. So they created this new abstraction called compute mode, which exists today. And the interface to the hardware is the following now. It says you write yourself a little program, like some function foo. In this case, I call it my kernel, because often we call, like in a data parallel sense, the code you run is called the kernel. And then you say, I want to invoke n copies of this kernel. You just, GPU chip, you figure out like how to do that, but I just want this kernel run n times. So what programming model is this? This is classic SPMD programming. I'm going to give you some code. It's going to have a thread ID in here somewhere, and we're going to launch n copies and run n copies of this. So you can think about this as like, similar programming model to something like ISPC. And that programming model is what's embodied in what's called the CUDA programming language, which in modern GPU programming is basically C, C++, with the one exception of you don't create threads. You just say, here's my program, please run n copies of it. And then the GPU says, okay, I'll go figure out how to parallelize those copies however I wish. Yes?
Could you just contrast this again with what we were doing before? Before it was just computing two triangles and it wasn't in an SPMD fashion.
Yeah, I mean, the difference from before, it was literally you would open up OpenGL. And you would say, OpenGL, draw these triangles in these positions, and you would set up the positions very carefully so that every pixel on screen was covered. It was just, it was a hack. Yeah. So now they're just like, let's use proper SPMD programming abstractions to essentially do the same thing. Yeah, exactly. Okay, so here's the plan. So that's just some history, and that's how where we are today with CUDA and why. So I'm going to talk a little bit about this programming model. And while you're thinking about it, I want you to think about, is this, should I be thinking about this as data parallel? Should I be thinking about it as SPMD? Is this message passing or a shared address space? If you had to organize this in your head, how would you draw analogies to ISPC and some things that you know? Okay. And I'm going to describe, since we're talking about CUDA today, I'm going to use CUDA terminology. So when I talked about ISPC, remember I said there was like a gang of program instances, and you kind of thought about program instances as a thread logically, but you kind of knew under the hood the implementation was not like a hardware execution context, it was a little vector lane. In CUDA, a program instance in ISPC is called a CUDA thread. So when I say thread in this lecture, unless I'm being careful to say like hardware execution context, I mean a CUDA thread. And a CUDA thread is whatever NVIDIA defines it to be. Okay. All right. So here we go. So just like in ISPC, when you called an ISPC function, you launched a gang of program instances, and the number of instances in the gang was n. It was kind of set at compile time, usually 8 or something like that. Right? And when you called ISPC tasks, you said that I'm going to run this function, I'm going to run this code, and I need to run it n times. Okay. So when you're programming CUDA, you're going to basically think about it the same way. So here's a call from regular C++ code, which says, I want you to run the CUDA function matrix add. And to be honest, and I want you to run it given these arrays as input arguments. A, B, and C are just normal C-style arrays. And the only thing that's kind of funky here in this weird bracket syntax is instead of saying I want you to run it n times, the number of instances you create is this multi-dimensional value. And the reason why it's multi-dimensional is just because it's sort of convenient for graphics and tensor operations. It can be helpful to say, create n threads, but organize them like in a 4x3 grid or something like that. Okay, so in other words, thread IDs are going to be multi-dimensional. And the one additional detail is that the instances are grouped into these blocks. So what this code does is I'm creating thread blocks of size 4x3 threads. So I'm getting 12 threads per block. And I'm creating a total of, the number of blocks I'm creating is 12 divided by 4 and 6 divided by 3. So in other words, Imagine I'm going to add, element-wise add 2 matrices that are each of size 12 by 6. And I want every CUDA thread to kind of take on the job of adding 1 element. So I need to create 72 threads. Okay. Now, here I decided to just say, instead of just creating 72 threads and saying create a 72 threads, I just said create these thread blocks where each thread block is 4 by 3. And the reason why I'm illustrating that now is I just want you to know about the concept of thread blocks so it comes back later. If all I was trying to do in practice of adding 2 arrays, I might have just chosen to say that they're 1D thread blocks, and I'm just going to have 1 block of size 72. Okay. So here's some basic CUDA syntax. The code I showed on the previous slide is what's up here. That's like main.cpp, calls the CUDA matrix add function. It does so with a certain number of thread blocks. And then the CUDA matrix add function looks a whole lot like an SPMD program that you're useful with ISPC. The only difference is instead of program count and program index, there's these built-in variables, block index, block dimension, and thread index that allow you to kind of figure out your unique thread ID. Okay. So in this case, thread ID is the ID of the thread in the block, like 00, 10, or so on and so on. The block ID is the block. And then to know like your unique position, you need to know the size of the blocks. So you can kind of think about it as your thread ID in the block is kind of like your program instance ID, your program instance. The block ID is kind of like your task ID in ISPC. So there's like this level of hierarchy is that instead of like ISPC organizes things into tasks and gangs inside the task, CUDA organizes itself into thread blocks and then can create many thread blocks at the same time. Okay, no new concepts, just kind of some different names and some small differences in the details. And so if you look here, this is a CUDA function called matrix add. The first thing it does is every thread computes which element of the input arrays it is responsible for based on its thread ID and its block ID. And then every thread carries out the work that it's responsible for. And keep in mind that in my program, 72 instances of this function are being executed concurrently. So the entire array is added together. Each thread copies or adds 1 element, and I create 1 thread per matrix, per element of the matrix. Okay, so there's some questions. So let me get to that.
Yeah. I still don't understand why did we move to a 2D system of...
I'm showing you the 2D system in these slides because it exists, and I kind of want you to know about it. I could have done all of these intro examples as thread ID and block ID being one-dimensional, and that would have worked just fine for this example. It turns out that in a lot of things that we do on GPUs, image processing, tensor processing, graphics, it actually can be a little bit helpful to have your thread ID be two-dimensional, because then you just go IJ. Whereas if your thread ID was one-dimensional and then you had to compute your location like in an ND tensor, there would be a lot of divides. So actually you can skip a lot of divides by giving you the multi-dimensional location, and so you can compute your memory address more efficiently. So that's the history of that. Yeah, but it's not fundamental at all. And every year I consider changing these as the initial intro to be 1D thread IDs, but then I have to introduce 2D later, and so I just decided to save some time by doing that. Okay. So at this point, you should be thinking about the kind of two worlds to live in. There's the world that's running the normal C++ code over here. That's like void main, and you should think about that as running on a thread on the CPU. And then there's the world that runs all of these instances of matrix add. And in ISPC, that's where we said, oh, it's a gang of program instances. In ISPC, we said the implementation was SIMD instructions in that same thread. Now, without getting into too many implementation details, the implementation of running all of these CUDA threads is actually going to be execution on the GPU. So that call of matrix add double B here is the point at which in the underlying implementation, if we get into that, that's going to be the communication to start running things on the GPU. Yep.
Could you in the previous diagram point out what the block dimension is?
Yeah, sure. So for reasons that don't seem necessary in this example, I have organized my code. Instead of just saying launch 72 threads, I have said launch a certain number of thread blocks, and each block is a 4x3 grid of threads. So the thread ID is two-dimensional. Those are these numbers. The block dims are not on this slide, but the block dim is 4x3. And then the block index is whatever the current block is. So it's just a multi-dimensional addressing there. Okay, make sense? Okay, so the CUDA memory model is I have like void main, presumably running on the CPU that has its own address space, and in simplistic CUDA, then there's the device, the GPU side of the world, that has its own memory address space that can be accessed by the CUDA threads. Okay? So that means that if you allocate an array in C and try and dereference that pointer in CUDA, that won't work because these are in different address spaces. Okay, so here's an example of this code. Here's my void main running on the CPU. I allocate an array a normal C allocation. That's an allocation in your CPU address space. Then I allocate, CUDA malloc. Then I allocate an array in the GPU side of the fence, the device address space. And then I use library calls to move the values from the CPU address space to the GPU address space. And then when I call a CUDA kernel, I pass it the pointers to device A, because the CUDA kernels running on the GPU need to access the memory in the address space of the GPU. This is kind of nuts and bolts CUDA. Now these days, it's on more modern systems, it's easy to actually just directly pass a C pointer into a CUDA kernel, but it actually means that your GPU memory access is actually going to go over PCIe and things like that. So I want to stick to kind of straightforward separate address spaces for now. Okay? All right, questions? Yes.
So, given that the memory is separate, like going back to the examples like cache, in this case, are there any situations where it's useful to like prefetch data from the CPU to the GPU, knowing like what computation to do?
Absolutely. So this CUDA memcopy right here is a movement from data. Now we're talking about implementation. Is a movement of data from CPU memory. And if we're thinking about a system that has a GPU that's like a discrete card, like a RTX GPU or an A100, this memcopy is actually moving bytes over the PCIe bus and putting it in the GPU's DRAM, two different DRAMs. So that's actually a slow copy, right? And yes, like there are ways to do that asynchronous and stuff like that. So what does this feel like actually in terms of, last time, didn't we talk about message passing? Kind of in some sense, this memcopy is a message pass from one address space to another. And you very well might want to do it asynchronously to hide latency and stuff like that. Absolutely. Yeah.
So going back to the previous example when we had matrix add, what we want is we pass in A, B, and C into this function, right? So we would want A, B, and C.
A, B, and C in this example are CUDA device allocations, right? They're not. And actually, I'm glad you brought me back to this example. Here's an example of I wanted to check everybody's understanding here. Okay, so this is the same matrix add example, but I changed the matrix size to 11 by 5. But I kept the thread block size to 4 by 3. I did this just for explanatory purposes. So I have 55 things to do, right? But I have thread blocks. I create work in the granularity of groups of 12 threads. So I have, if I round up, and if you look at my little math there for num blocks, I'm rounding up, which means I'm creating more threads than just 55 threads. So when each of these threads does this work to figure out its I and j, notice that some of those threads would actually be out of bounds in that array. And I have an if statement in the code to say, hey, this thread, check to make sure that you're actually responsible for valid work, and if you're not, don't do anything. So this really underscores, it should underscore, that this is an SPMD programming model. You're just creating threads, and the threads use the program to figure out what they're supposed to do. You are not doing something which says for every element in an array, launch a thread. That's not the programming model. The programming model is you launch a thread for all your blocks and for all your threads per block. And inside in my code, I might write some code that happens to do one thing per thread, or I could do whatever I want. Right? So that if statement there, what would happen if I didn't have that if statement? I would basically read and write to memory that was off the end of my array. Right? So who knows? My program would crash. Yeah.
So you're saying like the abstraction is that you're kind of creating threads, but it's just the implementation that's very different. Like CUDA versus like CPU.
Correct. The abstraction, to be precise, is you're creating CUDA threads, right? But you're not creating them one by one. You're creating them with like a bulk thread launch. So it's like imagine you had a C++ API which said standard thread, create, but you gave it some parameters after that, which was like, I want 150 of them. But really it would be like, it's not only that I want 150 of them, I want 150 blocks of threads, and each block should be 4 by 3. So there's this bulk launch of threads. Okay? Now I haven't told you how it's implemented yet, other than the GPU is going to run those threads. Yeah.
So can you go back a few slides ahead when you were having CUDA parameters?
You were declaring CUDA.
Yeah, I know. What happened? There it is, yeah. Okay.
Yeah, so out here, like after you've done this CUDA memcpy function,
Yep.
you will, I guess, all the computations you will be performing will be on device A, right? Like all the
CUDA computations I'll be doing will be on device A, correct. And if in this code right here, like in this C++ code, if I said printf device A sub 0, convince yourself that that should segfault. Because device A is actually a pointer into an address space that I can't reference from here. Right? This is basically, this is low-level C code, so you can do that kind of stuff and mess up. Okay. All right, so the basics of the memory model is that you have an address space for your CPU threads. You have an address space for your GPU CUDA threads. And it turns out that you actually have additional address spaces in CUDA. We have a block of threads. And one reason why they have this concept of a block of threads is they say that, every thread block has an address space that only those threads can access. And every thread has its own local address space, like its own local stack that only it can access. So, local variables to a thread can only be accessed by the thread. That makes sense. That's like ISPC. But now there's like per thread block variables, which are kind of like uniform variables in ISPC, actually. But there's per thread block variables, and then there's overall device global memory that can be accessed by any thread with loads and stores. So you just see this organization that's popping up. You're kind of saying, here's a bunch of threads that are going to work together on something. Here's another group of threads that are going to work together on something. And to do that work together, they're going to have some shared space. Okay? And so hopefully you're starting to think, we're giving hints to the GPU on how to co-locate all these threads for locality purposes. Okay, so let's do some CUDA practice with one of the simplest things I can think of in CUDA, which is let's not add two matrices, but let's perform a simple 1D convolution. So I'm going to take the output is the average of the inputs in the same location. So this is a basic operation, image processing or signal processing. It's actually the 1D equivalent of a convolutional layer in a deep neural network, something that you might want to do. So look at the top of the slide, and I have illustrated the input and output location. And I have some red arrows there that suggest what input elements are needed to compute every output element. So first of all, confirm that you agree The input is 2 elements bigger than the output, so I don't have to worry about any boundary conditions or crap like that. Just keep it. Okay. So here's the code for that. So first of all, we create, we call the convolve CUDA kernel. If the array is 1,024 in size, let's say the array is 1,000,000 elements, 1,024 in size, I decided to create, if my block size is threads per block, notice that I'm spawning n over threads per block blocks, assuming that that divides evenly. Just keep my integer math. And then for every thread, we just treat it as a 1D array index, in this case. And I say, okay, I'm going to compute my index that I'm responsible for computing. I'm going to load 3 values from memory, multiply them together, and output the result. So first of all, confirm that this is a correct implementation of a 1D convolution in CUDA. I will produce 1,000,000 or 1024 squared output elements. Okay. All right. So far in this example, there was really, I didn't use the idea of threads per block really at all. Like, I really would have preferred a programming model which said, get rid of all this stuff, just say launch n threads, and I'm good. Like, I don't have to deal with any of this blocking and stuff like that. Okay, so if you look at this code, every thread reads 3 elements, and different threads, like kind of neighboring threads, actually overlap in the elements that they read. So in some sense, this thread is issuing load instructions for data, and then the other thread is issuing load instructions for the same data. Now, maybe there could be some cache hits and stuff like that to amplify that. But if we really wanted to write an efficient program, let me show you something else that I can. So here's a much more complex program, but gives you a sense of what you can do with this idea of a block that has memory local to the block. Okay, so the same thing down here. I'm still launching the same number of thread blocks. My thread block size is what? 128 here. So to compute 128 outputs, how many inputs do I need? 128 plus 2, right? I need 130 inputs. So now look at what my thread does. My thread allocates this shared array of 130 elements. And that prefix, that type modifier shared, is saying this is not a per thread allocation. This is a per thread block allocation. So this is kind of like a uniform variable in ISPC. Okay. And now look what the threads do. This is kind of interesting. So every thread loads one value. If I go right to that first line, index equals, so I compute the index, and then the first line of code in the block is copying a value from the input array into this shared allocation. So the first thread in the block computes something and then copies that value into that shared variable at address 0, at index 0, and so on and so on. And then I say if the thread index, and remember that's a block local thread index, is less than 2. So in other words, if you're thread 0 or 1 in the block, what do they do? They move the last 2 elements. So I have 128 threads in the block. Every thread is responsible for grabbing one piece of data from memory and putting it in this shared array. And then because I need 130 things and not 128 things, I had to have 2 of these folks do a little bit more work. It's a little ugly. And then ignore this for a second. And then every thread just does what it's supposed to do. It computes the convolution, but instead of accessing main global memory, it accesses this local support, the shared variable. Okay. Now this is the last little piece of this, and that sync threads is the equivalent of a CUDA barrier within a thread block. So remember, all these threads, it's SPMD, they might be running concurrently. All the threads cooperatively load some data into this shared array. They barrier, which is waiting for all the threads in the block to do their share of the work. And then once they know that all the data is there, they run completely again in parallel, independently, computing their output element. Okay. So this is kind of an interesting thing about, like, why did I spend all this time like orchestrating this computation? Well, the reason is that these shared variables are backed by storage that you can think of as a high-performance L1 cache. Okay. So what CUDA knows, and now I'm talking implementation, is that it's going to put all the threads on the same thread block, kind of on the same core. And those threads can now access this fast local memory whenever there is reuse. So this code is actually saying that, look, no thread accesses the same data twice. Every thread, no one thread ever reuses data. But one thread uses data that its neighbor also uses. So we cooperate to bring all that data in once, and then we do our work running out of a really fast shared memory, or local memory. Yes, sir? Yep.
Why do you need the sync threads? Can you not kind of say, hey, I've loaded this small bit, and then let's run the computation from the small bit?
This is a great question. I want us to think about that as a class. If I remove that sync threads call, why could my program be incorrect?
You could access thread, the access to memory addresses that have been uploaded into the shared process.
That's right. So there's no guarantee in what order a GPU is going to run this code. It's just all these threads are potentially concurrent. So one thread might load its data in and then immediately start doing the computation, but we don't know if all the other threads has brought its data in yet. So that sync threads is the barrier which, when you proceed past it, you're guaranteed that this shared local memory has been initialized properly. Good question. Yeah.
Why do we need a separate thread local memory and a block memory? Why couldn't we have a large block memory?
Oh, I mean, I see. So you're saying, why do I have local variables like result? I think I wouldn't necessarily stress too much about it. I mean, it's pretty, I feel like it's, clearly the programming model needs to allocate thread local variables. And then so by default, everything is a thread local variable. There's a copy per thread. And then there's also the ability to allocate once per block variables. Yeah, so where these variables get allocated, like the implementation could allocate these in a piece of memory that's a big block for all the threads and stuff like that, but that's up to the compiler. But conceptually, it makes sense that I need private variables that are private to my own thread's execution, and I might need shared variables as well. Yes, sir?
These threads run in SPMD fashion, right?
This CUDA code is SPMD, yes.
The GPU will try to look for instructions that are same across threads and try to run them together.
SPMD, you're confusing with SIMD. SPMD is a programming model question independent of the implementation. So like ISPC is an SPMD programming model. CUDA is a SPMD programming model. What that means is I write one program, like this program right here, and the system will run it many times with different thread IDs. Now, how we execute all of those threads or all those instances efficiently is up to the implementation. And ISPC use SIMD instructions to execute things very efficiently. I have not yet told you how the GPU implements things. And yes, there will be SIMD involved, but it's a little bit different. Yeah.
Is it up to the programmer to pick threads for mods?
It's completely under your control. Like in the same way that it's up to you to figure out how many threads you want to launch in C++, here it's up to you to figure out how many threads you want to launch, but it's also up to you to tell the system how you want to organize them into blocks.
Always be the number of threads that a single core can run?
Well, it cannot be. Let me tell you this way. You are not allowed for it to be more threads than a single core can run. Can certainly be less, because I can put multiple blocks on a core. Yeah.
In this case, we were able to do this block data reading because we're reading data from the same part of the memory, exactly the 3 items. But if we're reading, say, something like a matrix, and you want to read the column of the matrix, would it be more efficient to do the same thing when you're reading
per block memory, or would you want to read it, say, by well, all I'm asking is does it matter if you're reading contiguous in block or?
It will certainly matter your performance, absolutely. The nice thing here is that all these threads are accessing consecutive memory addresses, and you can imagine that's going to be quite friendly under the hood. But if they were accessing, they're certainly it's possible they could access arbitrary memory addresses and bring them in. The program would still work, but obviously the memory system may provide lower performance because of cache locality and other things.
And so do we have control over how like CUDA malloc stores memory?
Well, you have control over, like when you ask CUDA malloc for data, it will allocate you a continuous part of the address space, just like malloc does in C++. How you lay out and place your matrix elements in that block of memory is completely up to you, is how you wrote that program. Yeah. Here I'm assuming contiguous row major, but that was my choice as the writer. Okay, so unlike ISPC, you actually, how like ISPC had those cross-lane operations to sort of communicate with some of the instances? CUDA has a variety of synchronization constructs. It has like a per thread block barrier, it has atomic operations, and then of course there's like actually synchronization that you have to do between the host and the device, like start these CUDA threads, wait for them to be done, and stuff like that. And you'll run into all of that on assignment 3. So the programming model for CUDA is an SPMD programming model where you write a single program that defines what a thread does. What a thread does is based on its thread ID, its block ID, and so on and so on. Those threads can synchronize in a block with some barriers if they so wish. When I launch threads en masse for a large number of threads all at once. Okay? All right. Okay, so now let's start thinking about implementation. So take a look at this program. This is the same convolve program as before. Exact same thing as the previous slide. Thread block size is 128. But look down here in the host code. This is the C++ code. And I decide to create about 1 million threads. And if you divide 1 million by 128, it's about 8K thread blocks. So how do you think this is going to be implemented? Do you think NVIDIA is going to launch? Like semantically, this says we need to run 1 million CUDA threads. Do you think it's actually going to go try and find 1 million thread contexts to run these with? Why not? Probably doesn't even have that capability, to have that many execution contexts. So what does this like big bulk launch remind you of? Yeah, it feels a lot like task. It's like I'm going to give you a whole bunch of work. Like do all of these thread blocks. That's all the work you got to do. And just like an ISPC task breaks down in the program instances, CUDA thread block breaks down into CUDA threads. Okay, so we want to be able to run this thing without the user. This code should work regardless of the number of cores you have or the number of your SIMD width and so on, right? We want this thing to work on a big GPU with a bunch of cores or a mid-range GPU with a small number of cores or like a Grace Hopper chip that costs $100,000 or whatever it is these days. That's what we want it to run on any of these things, okay? All right, so now let's talk about implementation. Okay, so here's our program again, host, CPU code, device code. And when I compile this device code now, I not only get the instruction stream, but I also have a little bit of metadata about what it requires to run. I might have something like it says, oh, well, I need 128 threads per block because that's what the programmer asserted I needed. It also says that, if it's 128 threads per block, it means that shared allocation is 130 elements wide, right? So I know that I need 130 floats, right? I need 512 bytes of storage in order to do that allocation. So I know I need 128 threads worth of resources, and I need 520 bytes of storage in order to actually run this thing. Okay. All right. So what's going to happen is imagine we have a little GPU here, has 4 cores. Let's not think about the details. But I just created those 8,000 thread blocks up at the top. So you're pretty good at this now, or at least for those of you that have been doing a little bit of thread pool stuff. How's this going to work? You just got all these tasks, all these thread blocks, and you're just going to go whoof, 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 to all your different workers. And by the way, in CUDA, you could actually set up dependencies between some of these thread blocks. But instead of what you're doing in assignment 2 and writing some software that decides what worker threads get what work, what you're doing in assignment 2 is embedded in GPU hardware in silicon. So The API that you're implementing in assignment 2, like run this task this many times, remember, that's the interface to the hardware now. So the interface is not, here's a program, here's a PC, start running it on this thread. The interface to the hardware is, here's an instruction stream, a program binary, please run all of these thread blocks of it. And in the hardware, right at the top of the GPU is something that says, oh, I have to run 8,000 thread blocks, I've got 4 cores, let's get to work. Okay? So this is another instance of this design pattern of you declare independent work and you let a scheduler assign it to workers. So let's talk a little bit about those workers now. So I'm going to give you diagrams for a Volta V100. I will, at some point later in the week, once I get done with one of my own personal deadlines, and once you get into the CUDA assignment, just for kicks, I'll go ahead and make a few slides on what like a modern Grace Hopper chip looks like. But it's pretty similar. Not much has changed since then. So, okay, so I want you to think about like basically like a mini little GPU processor, a GPU core. And it's got a fetch and decode unit at the top, like we're used to. And ignore all the rainbow colors here. Off to the side here are 16 ALUs that have to run in a SIMD fashion. Okay, so that's again my orange boxes. So that's the 16 execution units. And then here I have all of my execution context storage. Now, I'm drawing it this way a little bit different for a reason. Is I want you to think about it. Here's the storage for thread 0. So R0, R1, R2, R3. Here's the storage for thread 1. Here's the storage for thread 2. Here's the storage for thread 31. And I'm going to keep going and going and going. So I have execution context for, at least in this diagram, 128 threads. Right? Yeah. Heavily multi-threaded chip. 128 threads now of execution context. I have no superscalar in what I've drawn so far. And I have execution units that are 16 wide SIMD. Make sense? And the reason why I have other things, this is floating point execution SIMD. It could also do an integer operation SIMD. It could also do some weird funky math like in 8 wide SIMD, like trig functions and stuff like that. It can also do loads and stores. So just imagine there's a whole bunch of different types of SIMD operations that the thing can run. And this is actually called like an SM subcore. They use, that's their terminology. Okay, so these are scalar registers for one thread. Okay, now remember we talked about SIMD on a CPU, we said vector registers. So these are not vector registers, these are scalar registers. The execution context of an NVIDIA thread is a bunch of scalar registers. Here are scalar registers for thread 2. So 2 different execution contexts. Okay. Now here's the one major difference between how SIMD execution works on CPUs and how SIMD execution pops up on GPUs. So on CPUs, if we had a thread and it ran SIMD, the compiler generated SIMD instructions. On GPUs, because it's SPMD interfaced to the hardware knows that it's running n copies of this program. Okay? So what it's going to do is that every single thread here has its own program counter. It's one of the registers. In the event that 32 consecutive threads are on the same program counter, that same instruction is going to get executed in SIMD by all the GPUs. So it's all the same idea. There's just a small implementation detail difference. Is that on CPUs, the compiler generates that SIMD instruction. On GPUs, I have all of these CUDA threads that are all running the same program. If they all happen to be in the same place, the GPU goes, oh, let's run them with my SIMD unit all at once. So this is called like implicit SIMD. But at the end of the day, it's the same idea. And one way you can think about it is you can think about it as, up until very, very recently, especially in this older GPU, the only way to run multiple threads in SIMD is if the threads with consecutive IDs had the same operation. Like NVIDIA would never take a thread from here and a thread from there and run these SIMD. So effectively, a group of 32 execution contexts is kind of like a CPU thread with vector registers. You see how it's basically the same thing. And NVIDIA calls this concept a warp. So a warp is a block of execution context for 32 CUDA threads that when those CUDA threads are doing the same thing, those 32 CUDA threads actually get SIMD-like execution on this hardware. Okay. So threads in a warp are executed in a SIMD manner if they're at the same point in the program. And it's up to the hardware to identify that it's the same point in the program. They just basically compare PCs, and if all the PCs are the same across all of the threads in the warp, boom, 1 clock SIMD instruction. Yes?
You said there are 16 executions.
Yeah. Okay. So I just said that a warp is 32 threads, and I've only got 16 SIMD ALUs. Something's weird here, right? Boom, boom. So it actually will only run an instruction every other clock. So it'll do that SIMD instruction as 16 wide on consecutive clocks. And you might be wondering, well, doesn't that mean that instruction fetch and decode is just idle every other clock? It's not, because on that extra clock, it actually starts dispatching instructions to the other things. Right? So they say, oh, we can actually get by with less instruction fetch and decode. We'll issue a 32-wide operation every clock, but it means we don't have to fill that unit up again for another 2 clocks, which gives me some time to like issue floating point now and integer in the next clock, and then back to floating point, and so on and so on. So the instructions actually look a little bit like this. This is time in clocks. This is like instruction 0, instruction 1, instruction 2. And so the actual schedule of the processor is, let's dispatch this warp instruction. It takes 2 cycles. Let's dispatch the next warp instruction that might be I++ on all the threads. It's integer. And then 2 cycles later, we can dispatch back to the FP32 unit and stuff like that. This is all really low-level implementation details. It doesn't matter to the course, but I thought you might find it cool.
Are these schedulers intelligent enough? So this sort of is doing instruction decode and figuring out you have n number of units and having an execution. Like it has a buffer, right, to send it to that particular.
Yeah, for sure. I mean, this is your standard, in some sense, out-of-order pipeline processor. Yeah. It's actually pretty simple. It's not being that dynamic. It's just saying when I issue a floating point instruction, I know I can issue the next one in 2 cycles. It's not that hard. Yeah, that's not nearly CPU level sophistication. And so those different banks are, it's floating point ALU, it's 8-bit integer, it's 32-bit integer, it's load store, it's transcendental math. So basically that fetch and decode unit is just going down the program, the CUDA program, and going, look, all these, this block of 32 threads needs to run a floating point. Okay, this block of 32 threads needs to run integer. Okay, yeah. So that's just how it works. But the details are not super important. Yeah.
There are 4 PC or 128 PCs.
Every thread has its own PC. Every thread has its own PC. But you're only going to get SIMD if that PC is the same for everything in the warp. So it's effectively the same as if there were only 4 PCs. Effectively. But there are a few things NVIDIA could do with this abstraction, right? They could reorganize the threads to get better SIMD coherence for you if they wanted to.
I think they did that recently.
They only very recently, under some very limited conditions, they'll actually do that, right? So they're, in some sense, it 99% of the time behaves like a 32-wide SIMD machine with 4 unique PCs. And you can think about like as a warp as basically like a conventional thread with vector instructions. But that's actually not true. There really are a different PC for every CUDA thread, and this chip is dynamically checking to make sure that the PCs are all the same before it actually uses the vector instruction.
So can you elaborate where that 4 came from? The 4 PCs?
Oh, like in this diagram, I have execution context for. Oh, sorry, I expanded myself now to 60 warps worth of execution. That's a lot of execution. But no, that's actually true. But let me just go back to this this diagram. This will be better. Hold on. Oh shoot. Okay, there's a reason why I'm doing that. I'll tell you in 1 second. But really, there's 16 of these warps. So there's 16 times 32 execution context here. And that's how many PCs there are. But there can only be one of those uniquely executing at once. Yeah.
So a warp is like a collection of threads.
A warp is a hardware implementation detail. It's a collection of threads.
So how is a warp different from a thread block? Or like, is there any relationship?
Because a thread block is part of the programming model. A warp you never see. All you saw is you created 128 CUDA threads, and NVIDIA is going to use 4 warps of execution context to actually run it. Okay, let me put it all together. Again, like we're not going to do any of this stuff on the exam. I just think it's kind of fun to nerd out on this a little bit. The actual core of this chip is this thing replicated 4 times. Okay, so now this is why I was numbering my execution context this way. So there's actually this core, this big core, actually has 64 warps worth of execution context. So that's 2,000 CUDA threads, right? 64 times 32. Now it's got 4 different banks of these vector ALUs. And it's got 4 different instruction fetch and decodes. So this is all one thing. And it's got like shared memory attached to all of this. So the way it actually works, you can think about it as we have superscalar 4 wide, and every clock, every instruction fetch and decode tries to find a warp to run and runs it. In practice, it's a little bit limited. That fetch and decode is only going to pick amongst these warps. And this fetch and decode is only going to pick amongst these warps. So you can think about this almost as like 4 separate cores, but it's actually not true because all these execution contexts share the same shared memory storage. So you could create a thread block on this chip, to your question earlier, that has 2,000 CUDA threads and has 128 kilobytes of shared storage, and that would occupy this thing. And then this core, which is called an SM, would actually do 2,000-way multi-threading of those 2,000 CUDA threads. Every clock, it could actually make progress on up to 4 warps that it selects from any of the 64 warps that are available to it. There's a ton of latency hiding here. But notice, there's no new concept here, right? Like it's multi-threading, SIMD, and actually simultaneous multi-threading and superscalar coming from the instruction sections. Yep.
Sorry, just to clarify, so you said 4 warps, but we have like 4 quote-unquote cores, so it could be 16 at a time, right?
No, just think about only what's on the slide. Every fetch and decode is going to choose a warp to run. So I can only run 4 warps at a time, right? Or any one clock, I'm dispatching 4 warps. I'm gonna maybe 1 warp runs here, 1 warp runs here, 1 warp runs here, 1 warp runs here. Mm-hmm. So it's like I can make progress on 4 warps at a time, but I've got 64 to choose from. It'd almost be like a processor that can run instructions, like an Intel processor can run vector instructions from 4 threads at once, and it had 64 hyperthreads to choose from.
You're not running the entire warp, right? Because there might be some threads with the same program counter and other.
Yeah, I'm selecting a warp and running, I'm finding all the threads of the same PC and running it. Otherwise, I'm masking. Same SIMD mask stuff. Yes, you're right. Yeah.
Right, sorry, you keep saying PC. I might have missed it. What is PC?
Oh, sorry. PC is just there's one register here in any program, which is the program counter. And that's like the pointer to the next instruction to run. So the way to think about it is you look around and you look to say, okay, this warp, like all of my different threads are all at the same point in the program. And they're all runnable. Let's go dispatch this warp and use the SIMD ALUs to do it. Yeah, exactly. Okay. I want to move on because I don't want to get too in the weeds for too long here.
I'm just a little confused. What's the advantage of not having a SIMD and like having a swap concept? Like you can run it in SIMD, but not always.
Well, it behaves exactly like the SIMD that you know, right? If all the threads in a warp don't have the same program counter, we're just going to run all the ones that do, and then we'll run another instruction that runs the other program counter. So it'll behave just like you're masking from assignment 2. The only difference now is the hardware is figuring that out for you. You are not asserting it at compile time what runs together. So NVIDIA is leaving themselves the option to, in a future chip, change the SIMD width to 64. If Intel changes their SIMD width, you have to recompile your code because your binaries say This is an AVX instruction with SIMD width 8. They want to allow themselves to change that SIMD width in some future chip, and your code will still run because it's all just scalar instructions. They want the ability to reorder the operations to improve coherence for you under the hood if you have divergence. And they do a little bit of that sometimes. But for most code, if you just think about it like straightforward SIMD that you know, you'll have a great model of how it works on a modern GPU. Yeah.
Like you were talking about the user being able to use the block size, but let's say across NVIDIA architectures, they make some changes. If the user thinks...
Correct. If you put something in your program, you are asserting that the hardware has to handle it. So if you, let's say on this particular processor, you could create a block size of 2048 threads. Because I can fit 2048 CUDA threads here, and they can all have access to the same shared memory in the block. Earlier GPUs had a maximum number of execution contexts per SM core of like 256. So you could not have it will compile time fail. You cannot run this program on this GPU because your program needs 2,000 threads per block, and this GPU can only support 256.
But at the time of writing the program, let's say you wrote it for the previous architecture, it's not going to scale the way you just spoke.
Correct. So now it's not as big. Like if I wrote a program that used 256 threads per block, and then NVIDIA comes out with a new GPU that supports 2,000, I could change my program, or I can just keep it the same, and NVIDIA might be able to run 4 blocks per core. Yeah, exactly. So yes, I might, whenever you start manually scheduling something yourself, you're making assumptions about what the hardware can do. Right? And that's what NVIDIA is saying here is, we prefer you not to manually schedule the SIMD, let us do it, because we might change the block size. We might want to reorder things for you, and we'll do it better than you will sometimes. Yeah, cool. Okay, so to wrap this section up, let's go back to this code. Remember, this is something that has 128 threads per block and needs 512 bytes of storage to run. So when CUDA says, oh, I need to run this thing on a core, it will take this thread block, allocate 512 bytes out of the shared memory here, and allocate how many execution context, or how many execution contexts? 128 threads, which actually here ends up being 4 warps worth of execution contexts. And I intelligently allocated them across the slices so that they can kind of run concurrently. Okay? Now this diagram here, what you're seeing, is what NVIDIA calls the shared the streaming multiprocessor, the SM. And this is the block that's replicated 80 times on the V100. Okay? Right. And so if you just do the math, there's a 1.2 gigahertz clock, I think at normal clock speed. There's 80 of these things per chip. Each of these 80 has kind of these 4 columns, and those columns have 16 wide vector ALUs, right, for floating point math. So you multiply all those together, that's 12.7 teraflops of performance for floating point math. And if you do 80 times 64 warps per SM times 32 threads per warp, that's 163,000 concurrent live CUDA threads on the chip at once. So your Intel processor has support for 2 hyperthreads. This thing has support for 163,000 CUDA threads. They can't all execute at the same time, but they're all there on the chip at the same time. Yes?
Previously you mentioned that each thread's memory will get allocated in the shared memory, right? So
Those shared variables, right? So remember this program had that shared variable, shared float support. It says this thread block. So the shared memory is the place where you start asserting actual scheduling details as the programmer. So there's a compromise, right? Like CUDA said, you should just tell us how many blocks to run, and we'll run them however we wish. But they said memory is super important. So we're going to allow you to assert that I need 512 bytes of storage. And what NVIDIA is going to do, well, we're getting to that, is if we run this thing, it's going to run a thread block, it's going to choose warps, execution context on the same core processor. It's going to allocate that storage so all those execution contexts can read and write from it. And since all these threads are kind of there in the same core, things like a barrier between them will be very fast. Whereas if I happen to take some of the threads from this thread block and put them somewhere else on this machine. Over here, imagine a barrier would be communication across all of these things. So the thread block is the granularity of synchronization and data locality when you're writing a program.
That means that the amount of data memory that has the output has to be known at compile time. Like you
For shared memory, yes. Now, and I'm giving you a simplistic version of CUDA. Like if you go to the modern CUDA docs, they're going to say, sure, you can call malloc on shared memory also, but then there's going to be some, it gets harder. So I want to give the simple version first, right? So let's talk about running this thing. We create this, like we write a program. We have all of these thread blocks. We need 512 bytes of storage. And let's imagine a very simple GPU. Not the thing I just showed you, but a very simple GPU, which can run one instruction per clock, actually has 32 wide SIMDs, so I drew it out, and has execution context per SM core for 384 CUDA threads, which is 12 warps. Okay. So what do you think is going to happen? So we run this thing. We say, okay, we need 8,000 thread blocks. You're implementing thread queues or thread pools. You know how it works. You're going to say, I need to execute this task, this convolve function. My arguments are this, and the number of blocks are 1,000. Okay. And my GPU work scheduler, just like probably very much like your implementation, says, well, first thing I'm going to do is I'm going to allocate 128 execution context over here. I'm going to allocate 512 bytes of shared memory, and I'm going to increment my next pointer to 1 because I've already dispatched one of these thread blocks. Okay, what happens next? Scheduler, can it schedule more work?
Yeah.
Absolutely. So where do we put it?
The other one.
Probably should put it on the other core, right? So the next thread block comes out. We execute it, or we allocate 128 thread blocks. We grab 512 bytes of storage. We're good. Now the next task is, or sorry, the next pointer of the next thread block is 2. Can we keep going? Now we can. Let's schedule the next block. So now notice multiple blocks are being scheduled on the same processor. I've got a ton of execution context. So now I grabbed another 128 execution. I grabbed another 512 bytes. Let me go ahead and fill this thing up with the 4th thread block. And now the 5th thread block cannot be scheduled right now. I do not have the resources. Why do I not have? I actually have the execution context, but I actually didn't have the shared memory. In this example, I only had 1.5K of shared memory. So NVIDIA is going to not schedule things that it knows it can't fit. So we'll just wait. And at some point, one of those thread blocks finishes. When that thread block finishes, some resources are available, and now let's schedule thread block 4. And now notice that since this is SPMD and all of these thread blocks use the same amount of resources, it's pretty easy to just, whenever someone finishes, the exact amount of resources are free to start a new thing. It's like kind of very homogeneous resource requirements. You don't have to solve an allocation problem or anything like that. So that's why it's nice to know the resources up front. Okay? So things will just keep going and going and going and going and going. Right? And that's what the NVIDIA GPU is going to do. So let's check our understanding just a little bit in the last 4 or 5 minutes of class. Okay, so if you understand the next 3 slides, you are really thinking through step by step. You are in your head going through, okay, I can just play out in my head what the implementation is doing. Okay, so here's an example. Okay, so now I made a core, and this is not the full thing. Notice that let's just say it only has 128 execution context, so 4 warps here. I made a tiny little core. Okay? And I have my thread block with 256 CUDA threads. So I have a core that only has execution context for 128. I have a program that I wrote, 256. Why can't, so NVIDIA is going to say, sorry, you can't run this. But why can't it? Why doesn't it just run the first 128 threads on the thread block, wait till they finish, and then run the next 128 threads?
I think it's because the programmer has specified that the data locality is, you want that the full 256.
Okay, and that's sort of true because that's the rules of the programming model. But why are the rules of the programming model this way? Why don't they just say you can ask for as many threads per block as you want, and we're just going to run them, and we're going to run the first half of the threads to completion, and then we'll run the next half. I'm still going to give you your shared memory.
Yes, because based on what you know about the program, is going to run more efficiently like that way.
That's true. I mean, what you're saying is that if the programmer told you to do something, it's good in a system to do it. But there are a lot of times when the underlying system implementer says, I think I know better. As long as I can do it correctly, I'm fine.
Because of like synchronization.
So look at this program. It has a barrier in it. So that barrier says that we will not proceed until all threads get here. What if we ran 128 threads, they stall at that barrier, they're still having those execution contexts, and what happens? Nothing. They never yield them, and so the other threads never get a chance to run. So unless you start thinking about more advanced implementations where we're going to preempt these threads, rip them off the processor, put the other ones on, which would be highly not performant, this program's going to deadlock if I try and run it on this machine. So that's why NVIDIA says, look, like we're a high-performance programming system. If the programmer decided to do something, we need to respect their wishes. We don't want to do crazy things that might impact performance in a bad way just to get the program to run correctly. So standard CUDA is, you should think about it as no preemption, and things that would be magical are not done. And so this is why CUDA will reject this program. The idea is that the threads in a thread block are not just SPMD threads, but running concurrently at the same time, live at the same time on the same SM. Because you may do things like want them to cooperate with barriers or atomics and stuff like that. So this thing is busted. Okay. All right. Two more things. So this is like just a review slide. Let's think about this one. Let's think about a CUDA program that creates a histogram. I create a bunch of threads, and all of them, in whatever thread blocks they're in, just compute some value and then increment a bin. And CUDA has the ability to have atomic operations like atomic add. So imagine all of us are CUDA threads. We all grab a variable, compute some function, say, oh, I need to increment bin 42. So you go to bin 42 and do an atomic safe update. Is this a valid CUDA program? I kind of have threads in different thread blocks touching the same memory.
How can you like synchronize between the different thread blocks and throw on different SMs?
Well, imagine that this atomic add is atomic out to global memory. This is okay. Like I've done nothing here that makes any assumptions at all about how CUDA runs these thread blocks. You know, it's just going to run them whenever it wants, and they might contend for an atomic, but so what? So this is okay. This is okay. I'm treating the thread block as like I'm just going to launch as many as I need and execute them in whatever order you want. But now think about this one. Imagine a piece of code where I launch 2 thread blocks, and one of them says, okay, update this variable in memory, and then the other thread block says, wait until that variable is updated. So one thread block says, I did something, the other thread block waits for it. Imagine running this code on a GPU that only can run one thread block at a time. If it runs thread block 1 first, thread block 0 never gets to go, and thread block 1 is waiting all the time. So you see how there's a difference. Like these things, communication is possible, but you cannot make assumptions about the order in which stuff is done. So thread blocks need to be, they can interact, but they cannot make assumptions about order. Whereas threads, inside a thread block, you can assume that they're all running at the same time, and you can use barriers and stuff like that. Okay, I should stop here so you can go, but feel free to ask any questions.